Yeah, so Dan is an assistant professor in the Decision Risk and Operations Division of Columbia Business School, where he's been since 2017. Prior to that, he spent a year at Northwestern's Kellogg School of Management and a year at Microsoft Research. He got his PhD from Stanford in 2015, where he was advised by Benjamin Van Roy, and his research interests are in the intersection of statistical machine learning and sequential decision making. It's a great pleasure to have Dan here today to talk about his paper, Global Optimality Guarantees for Policy Gradient Methods. So over to you.
Okay, great. Thanks so much for organizing this seminar series and for inviting me. Yeah, it's an honor to present here. I'll try to heed your advice and keep the controversy for after the recording. We'll see how I do. Okay, so this is a joint work with Jalaj Bhandari, who's an excellent PhD student at Columbia in the IUR department. Okay, so as was mentioned, there's an incomplete working draft of the paper here. It's I guess linked on the website and also in the slides that are shared. Okay. All right, so I want to talk about policy gradient methods, which have risen in popularity in the reinforcement learning community. Okay, and the way I guess they're viewed by many students as they first hear about them is there's sort of a snippet of code that's compatible with TensorFlow or PyTorch or so on. And using that, you can sort of reduce dynamic programming problems to a kind of a gradient descent on a neural network. Right? And so these kind of snippets of code, and the idea here, if you link that with a fair amount of engineering and compute, you can use it to play a game like Pong. Here, controlling the paddle by learning a parameterized neural network that directly maps pixels of the screen to a stochastic policy that indicates a probability of moving up in this arrangement. Now, if you take this and you add to it a whole lot of engineering and a small data center, you can do very cool things like this kind of amazing demo of a robot arm having the dexterous motor control necessary to solve a Rubik's Cube. Okay. Now, from a more intellectual perspective, there is something really promising in a deep way about the way policy gradient methods go about solving sequential decision-making tasks. Okay, one is that they directly try to optimize the function you care about. So they directly try to minimize total cost incurred, in contrast to something like a model-based approach, where you would first fit a model, say trying to minimize mean squared error of your predictions, and then afterward, you would try to pick a policy that's effective under that model. Right? So there's something nice about being end-to-end in this manner. Beyond that, a sort of a central theme in this paper, the thing that's interesting to us, is that it feels like in many cases you might have a nice insight about the structure of an effective policy, and the nature of the effective policy might somehow be much simpler than something like the model of the whole world. Okay, and there's some tantalizing sense in which maybe policy gradient methods are effective when the policy class of interest is simple. Okay. So that's sort of the high-level motivation for looking at this class of methods. Now let's formalize some of what we're going to be studying. We're interested in direct optimization over a policy class by some kind of local search. Okay, so the central, so sort of fixing some notation, will denote cost to go functions by J sub pi. So this is the measuring the cumulative expected cost to go from any initial state S, where gamma here is the discount factor. Okay. Now, in classical dynamic programming, and you seek an optimal policy which is able to minimize cost to go in a strong sense. It minimizes it from every single initial state simultaneously, somehow solving a multi-objective problem. Okay. For what we'll discuss here, it's helpful to instead think about a scalar loss, which treats the average expected cost to go under an initial state drawn from some initial distribution rho. Okay. Now, clearly having a optimal policy in the classic sense from every initial state, that would minimize L. But in fact, the other direction holds as well, assuming that rho has full support over the state space. Okay. So in everything that follows, an important caveat is that we will be assuming rho is supported on every initial state. Okay. And now you can interpret this loss function as essentially measuring performance in a manufactured average cost problem, where in every period there's a 1 minus gamma probability that the agent restarts in a random state, and rho is the distribution governing the states at which the agent ends up after the restart. Okay, so this is just a classic dynamic programming thing. You can interpret discounted problems as a version of episodic problems.
So Dan, there was already a question regarding this full support. So like what happens if you don't have full support?
Good. So if you don't have full support, I guess I won't go into this in detail, but basically policy gradient methods, even if you use a stochastic policy, they don't perform intelligent exploration. And so what ends up happening basically is that there can be either literal points where the gradient of the policy gradient loss function is 0, despite the policy not being optimal, or just cases where the gradient is exponentially small, despite the policy not being optimal. So pretty much without
right,
this, there's a no hope of policy gradient methods reaching an optimal policy.
Right, but is that really related to learning and exploration, as you say, or rather to optimization? There's something in the landscape.
Good. So I think maybe what's interesting here is that, yes, you're right. I'm framing it as an exploration problem, but actually it also manifests itself in a landscape problem. Okay.
Right. Okay. Gotcha. Thanks.
Yeah. Thank you. It's a great question to start out. Okay. So now maybe the central object for interest of interest for us is not just this loss function L, but when we run a policy gradient method, we don't search over the class of all policies that I'll call pi. So here pi is the class of all potentially randomized Markov policies. So a policy pi maps a state to a probability distribution over actions. Instead, we're searching over a parameterized family of policy functions. Okay. Now, somehow intuitively, this parameterized family captures some inductive bias about which form of policy might be effective. Now, given this setup, policy gradient methods follow a very simple idea. We just run some version of gradient descent or stochastic gradient descent on L. Okay, iterating theta k plus 1 is theta k minus a step size times a stochastic gradient. Okay, for this paper, we're really going to be interested mostly in the structure of the loss function L, and we may, at times, it may be more natural to have some other related first order method like projected gradient descent in mind as well. Okay. So something exciting about this, in a way you could, so there's really a lot of methods for evaluating approximate gradients of L. Okay, there's a score function gradient estimator that's popular in the RL literature. So actor-critic methods. There's finite difference methods and infinitesimal perturbation analysis. There's many ways, in principle, where we could think of using to estimate gradients of L. Okay, but it's not really clear that local search on L makes sense. All right. So somehow there's something nice that we have reduced dynamic programming to something you can execute easily in TensorFlow. But it's not a totally satisfying reduction because this loss function is almost always non-convex. It's non-convex even in the simplest classical dynamic programming problems that would be treated in a course and can be solved exactly by other methods. And this is a somewhat fundamental, unavoidable issue, okay, that has to do intuitively with the fact that the cost to go is a multi-period objective, which means that small changes in the policy can essentially have a compounding effect over time because they influence the state distribution that you're at in future periods. Okay. Now, what's sort of understood then is that you'd expect even stochastic first-order methods to converge asymptotically to some kind of stationary point. Stationary points in unconstrained optimization are just points where the gradient of the loss function is 0. Okay, so we expect the gradient descent makes progress, makes progress, makes progress until some point where it gets stuck. Right? But for problems that maybe we otherwise could have solved through other algorithms, that's not totally satisfying because the literature provides almost no guarantees on the quality of the stationary points of L. And I'll show you in a moment an extremely simple problem that has very bad local minima. All right, so this is a real issue and not just an issue of analysis. Okay, so our scope is really going to focus on the optimization landscape of the loss function, L. Okay, and sort of a benefit of that approach is that it's not algorithm specific. And so you could think about many different algorithms that you might apply, versions of policy gradient. And in some sense, the landscape of L is relevant to all of those cases. At the same time, there's some loss of specificity by doing this. Okay. Now, so sort of for understanding this talk, you should really imagine, as we do, that you're in some kind of simulated or laboratory environment. And it's then providing kind of an idealized setting where exact or near exact gradient evaluations would be possible. It's nevertheless not clear that local policy search on L would reach a near optimal policy. And I think the central distinguishing feature of this work is that we're really interested in when the landscape of L is nice and how that interacts with the parametrized policy class. Is it enough that this policy class is somehow has regularity conditions and contains a near optimal policy? Or do we need some other kind of condition on the policy class? Okay. Just to make clear, this scope, I think, is broad enough to be interesting, but it's certainly not touching on all potential challenges that policy gradient methods face. Okay, so really our focus here is on non-convexity of this objective function that comes out due to the multi-period nature of the objective. Now, let me highlight that that's not, say, like non-convexity that comes from the parameterization of your neural network. It's something more inherent about the multi-period nature of the problem. Okay. Now, beyond that, there are at least 3 other major challenges with policy gradient methods. One is just a variance in the stochastic gradients, and we're imagining kind of that you average enough gradients, that's not a problem. Another is insufficient exploration, or as the question already got to, sort of how that distribution rho affects the landscape of the optimization problem. And we're requiring that rho kind of has nice support everywhere. Finally, there's issue of policy parameterization. This, I think, is not always in nature something to do with a multi-period objective, but instead has to do with the fact that the softmax policy itself has poor conditioning and requires often a local change of coordinates to be effective. All right. So in what follows, you should really think of the results as addressing issue 1. Okay. So before coming to the main insight, so not to spoil the punchline, I want to warm up and build some intuition by discussing good and bad examples for policy gradient, i.e. cases where the landscape of the optimization problem is somehow amenable to gradient methods, despite being non-convex. And then a case, and I'll start with, a case showing you that indeed the landscape of L could be problematic in even the simplest settings. Okay. So let's start. Here's kind of my dream result. It's that you could say that policy gradient methods will reach the global optimum if the policy class is somehow regular, so it has some regularity and smoothness conditions, and it contains an optimal policy. What this is somehow saying is that if your inductive bias is correct, if you manage to have a policy class that's well suited to your objective, and you specify that in a clear way, then policy gradient methods should be effective. I want to emphasize that because of the non-convex nature of the loss function, this is just not true. Okay. So here's a very simple example that I'm not sure is widely understood in the literature. Okay. So it's a 2-state Markov decision process. There's a left state and a right state. From state left, you can choose to stay left, incurring a cost per period of 1. Okay. In each period, when you're in state right, you could choose to stay right, incurring a per period cost of 0. Okay. The optimal policy is going to be to go right and stay right. Okay. But switching incurs a short-term kind of energy cost that's greater than the cost of being in either state and staying put. So there's a cost 2 of switching states. Now, the optimal policy, which is to go right always, whether in the left state or right state, and stay there. So this is optimal as long as the discount factor is moderately large. That could be encoded in a very simple one-dimensional policy class. Okay. So here I'm thinking of a stochastic policy, which in state left, so there's a cost 2 of switching states. Oh, okay, I heard an echo of me.
That was just an echo, yeah.
Okay.
I guess whoever is running the show should be muting this person.
Yeah, no problem.
Yeah, go ahead.
Sounded great. Okay, so so here, this policy assigns a probability theta to going right, regardless of whether you're in the left state or the right state. Okay, so this is a lower dimensional policy class than the set of all policies, but it's one that contains the optimum over here at the right, and a policy that goes right with probability 1. Somehow we've reduced our problem to searching over a simpler policy class. Unfortunately, the loss function is non-convex. So here you can see that there's a bad local minimum. If you were, say, if you started with a theta parameter less than something like 0.3, meaning that most of the time you go left, then local search will take you over to this corner here, a bad local minimum. Okay, and there's no reason to expect that any local optimization algorithm would avoid this kind of local minimum. Okay, so the essence of the problem, to have some intuition, is that if you started with a policy that almost always goes left, and then you increased the probability of going right, that would just hurt you. Because any moment at which you go right is followed very, very likely by immediately moving left again. And having moved right and then left again is even worse than having just stayed left in the first place. Okay. So the punchline here is, despite containing the optimal policy and being a very simple policy class, the policy class does not allow for local improvement. The natural question that everyone asks after seeing that example is, what if you add a second parameter, moving to the class of all possible policies? Okay. So let's consider that. Now there's a probability of moving right in state left, and a separate probability of moving right from the right state. So this is the full policy class. Now, in this case, policy gradient will reach the global optimum, despite the fact that the loss function is non-convex. Okay, one way you know the loss function is non-convex is because if you looked at a particular one-dimensional projection of the loss function, you get out this. You can also see that it's non-convex by looking at the trajectory that policy gradient takes. So here on the x-axis, I am showing the theta L parameter. And on the vertical axis, I'm showing the theta R parameter. You can see that policy gradient converges to the optimum, but does so through a very strange path. It first moves left, okay, diagonally to the left, seemingly in a direction that's not aligned with the direction to the global optimum, something that gradient descent on a convex function would never do. Okay. Now it moves over here, moves up. Eventually, once the chance of going right in state right is high enough, it starts increasing the chance of going right from state left. Okay. To spoil some punchline here, what's happening is that the behavior here looks a lot like what policy iteration would do. Yes, question?
So then I have a question here. So what you're showing here, this is the gradient flow with a very, very small step size, or there's also like a finite step size that you're using?
Precisely, yes. So this is so in the code, I think there is a small step size, but it's almost precisely the gradient flow.
Right. I see. Nice. Thank you.
Okay. So in some sense, this feels maybe okay to some people. The full policy class allows for local improvement, but I find this unsatisfying. Because somehow much of what we started with as motivation in the beginning is that if we have a strong inductive bias that a certain class of policies should be effective, allowing us to treat maybe complex problems with large state spaces, then policy gradient may be especially useful as a procedure. But here, we saw that when you have a strong inductive bias, policy gradient did not work. It was only with no inductive bias that policy gradient was working here. Okay. So if the story ended there, it would maybe be some bad news, at least for me. Okay, but there's some hope and mystery here. So I've shown you that policy gradient gets stuck in a bad local minimum in general. Okay, but there's no bad stationary point of the loss function for finite state inaction MDPs with the full policy class. This is something that we will prove in our paper. I think it probably was known to some others as well, but I am actually not sure of the first or the right reference kind of historically for this observation. I'll mention at least a couple earlier. Okay. Now, what really motivated this work for us is a kind of a very nice paper by Fazel et al. That studies global optimality guarantees for policy gradient methods in deterministic linear quadratic control. In linear quadratic control, you do have a strong inductive bias that a very special subclass of policies, the class of linear policies, contains an optimal policy. And now, gradient descent on that subclass of policies, they show converges rapidly to the global optimum. Now, the proof is, I think, impressive, but involves a somewhat intricate analysis of the various closed form expressions that are available in deterministic linear quadratic control. Kind of begging the question, what was special about linear quadratic control that was not occurring up in this bad example here? Adding to the mystery, in the operations literature, these authors provide global optimality guarantees for a stochastic approximation algorithm that searches over the class of base stock policies in an inventory control problem. Inventory control also has a large number of closed form expressions that are specialized to that case, and carefully analyzing those expressions shows this convergence to optimality. Again, we're left with this mystery. How do we reconcile the good cases and the bad cases and what's going on? Okay. Now, I should mention that many of these are classic dynamic programming problems of the kind that perhaps could be solved by other methods. My own sense here is that the right way to start studying and sanity checking something like a policy gradient procedure is to first make sure that it makes sense in problems that we know are solvable by other means. If it cannot solve problems that are easily handled, it raises some concerns about whether this procedure is really a good foundation for approaching very complex problems. Okay. So with that as motivation, I want to bring you to sort of the main insight and contribution of this work. The main contribution is going to be a set of general conditions that ensure the loss function L has no suboptimal stationary points. Okay. Under fairly broad conditions, like on the loss function L, first order methods, even stochastic first order methods, are guaranteed to reach a first order stationary point. This is a point satisfying the first order necessary conditions for optimality, and essentially a point from which the algorithm can make no more progress locally. When the parameter space theta is unconstrained, this just can be rewritten as saying that the gradient of L is 0. What we want to show is that whenever such a condition is satisfied, the landscape of the loss function is such that that means that the policy is itself optimal. Okay. These conditions will apply to several classical control problems, including the set of all stochastic policies in finite state inaction MDPs, appropriately parametrized, the set of linear policies in linear quadratic control, threshold policies in optimal stopping, and base stock policies infinite horizon inventory control. Okay. Now, yes.
Sorry, just a quick clarifying question. So I guess what's important here is that the argument on the left-hand side is really taken over the set of all policies, right? So it's not just in the policy class, but is the entire class of policies.
Yeah, thank you for highlighting that. So
Okay.
first, I think even if this were over the class of parameterized policies, it would be surprising given non-convexity.
Right.
But
yeah.
here it's actually not. It's over the class of all possible policies. Okay. Now,
right.
in some sense, these are the same in this case because here the class of parameterized policies does contain the optimum. Okay. Otherwise, I guess it would be impossible. It would be impossible. So now, a few things to mention here. One is that these are sort of simple problems, but they are some of the canonical dynamic programming examples of the form that are, say, taught in my graduate dynamic programming course as sort of the main examples. Now, another thing to mention is that in contrast maybe to some of the literature on this topic, this includes cases, for example, where the action space is infinite and per period costs are somehow structured functions of those infinite actions. Okay. So to be a bit more specific, maybe the main intellectual contribution is a particular condition we identify as being maybe the dividing point between the good and the bad examples for policy gradient, and specific kind of precise implications of this condition. Okay, so I'll spend a while sort of unpacking this idea, and then in a couple of slides, I'll discuss related literature. Okay, so what is this condition? Well, what it says is that over here on the right-hand side, I guess there's a typo here. This should be pi bar. What this is thinking of taking a Bellman update. So T here is the Bellman operator associated with the policy pi. Okay, and it should say pi bar again. So I'm asking, over here then is the Bellman update. The Bellman optimality operator is defined as the minimum overall policies here. And I'm taking the Bellman update by minimizing over the class of all possible policies. The special structure in some of the examples before is that in a strong sense, the set of parameterized policies is really sufficient for control in that the one period problems induced by considering a Bellman update can be solved within the parameterized policy class. Okay, so to make this more concrete, in linear quadratic control, can I just finish this sentence? And then, in linear quadratic control, if you start with a linear policy and you consider making a Bellman update to that linear policy, it's sufficient to minimize over linear policies and not over all policies. Yeah, okay, question?
Sorry. Is this the argmin or the min? And like, in what sense are we minimizing? Is this like a scalar quantity, this Bellman operator applied to the value function, or is it a vector quantity? Or?
Great. So in no, this is a bit imprecise, I guess. What
I guess like
yeah.
One step look ahead things.
Yeah, so what you'll see in a moment is a certain weighted version of a Bellman update where it's always, where this equality is always defined. The reason I guess this would be well defined here is there is a single policy over here in the parameterized class which matches the minimum simultaneously for every single state S.
Okay. Yeah.
So the optimality in the sense of like a policy iteration update. Okay, thank you. Okay. Now, let me highlight that this is stronger than requiring that the optimal policy is contained in the policy class. And we saw that that's necessary by that simple counterexample I showed you at the beginning. But at the same time, it's much weaker than requiring that the policy class is the class of all policies. Indeed, this is satisfied by simple examples like threshold policies in optimal stopping, where a much simpler class of policies does suffice. Okay. So having now sort of understood what this condition means, what are the implications? Essentially, if you think about the main lesson of dynamic programming, it's that these seemingly complex, non-convex optimization problems that consider performance over a long horizon can be broken up into much simpler single period problems that are involved in, say, making a Bellman update. Now, for closed policy classes, it seems that the loss function L of the infinite horizon policy gradient cost inherits the nice properties of those single period objectives. So this notation will be defined more precisely in a moment, but for now, just think of it as some kind of weighted cost function associated with a Bellman update. Right? A much simpler one period problem. Kind of the punchline of this work will be that if those class of Bellman update cost functions have no bad stationary points, then neither does L. Okay, and that's true for closed policy classes. Now, stronger conditions also hold. Sometimes, and in many of these examples, before, for example, the Bellman one-step cost has a stronger property like convexity. That implies something called gradient dominance, which leads to fast convergence rates for forced order methods. So the second main insight is that when this one period objective is gradient dominated, so is the non-convex infinite horizon cost function L. Okay. So somehow, even though policy gradient methods are not breaking the problem up into a sequence of single period problems, in the analysis, we can do just that. Right. Now, beyond that comment, these results are shown to approximately hold for approximately closed policy classes. In a way, I'll make precise. And some condition like this is certainly necessary, because we've seen that without one, policy gradient methods can get stuck in bad local minima. Okay. We make a couple of interludes. So I won't go into enough depth here, but certainly this is not the first paper to study convergence of policy gradient methods. And there's kind of a rich history in reinforcement learning that's related to some of these ideas, although maybe still less than I would expect. Okay. Some notable references. Thomas gives a very simple argument that for softmax policies, the gradient of the loss function is never exactly zero. Kakade and Langford set up a lot of kind of critical ideas that then lay the groundwork for policy gradient analysis. And this kind of underappreciated paper by Scherrer extends some of that analysis to policy gradient with convex policy classes. Now, this closure condition in the policy class, and especially the notion of approximate closure, is somehow a nice conceptual analog of something called inherent Bellman error, which comes up in the study of value iteration methods. Okay. Now I'll go into less discussion about this kind of more simultaneous related work, some of which is very impressive. I think that the central dividing line is that somehow relative to that work, this closure condition and its implications for the landscape of the loss function are new to this work. Okay. So with that, let's go ahead and make this closure condition and its implications more precise. Okay. And the analysis is going to go by thinking about a much better understood procedure, policy iteration. Okay. Policy iteration, unlike policy gradient methods, follow the classical kind of principle of dynamic programming of searching for an optimal policy by somehow breaking the problem up into a sequence of simpler one-period problems. Okay. So what policy iteration does is, starting with a policy pi k, it considers at each state S the Bellman update, kind of the one-step look-ahead cost to go associated with applying an action A for a single time step before following pi k thereafter. In RL, this is usually called the Q function. Okay. And it forms a new policy, an improved one, that attains the argmin on the right-hand side for every state S. Okay. Now, it's difficult for us to talk about this object because it requires solving a minimization problem simultaneously over every state S, okay, which isn't possible with constrained policy classes. So what we're going to do is define a scalarized version, which essentially averages this quantity over a set of states randomly drawn from a distribution nu. Now you could write this in one of two ways. One is as averaging over the Q function evaluated at a new policy, and the other as evaluating a Bellman update to the old policy. Those two are the same. Okay. Now, I want to just make this comment that these one period cost function associated with the Bellman update or with policy iteration is often much simpler than the multi-period loss function L. In particular, for finite state and action problems, where an action is just a vector encoding the probability that each deterministic action is chosen, the one period cost function is just linear. Okay, so it's certainly then convex and has no bad stationary points. It's L that's the problem. Okay, so now we're ready to state maybe the main result in this paper, which says that under mild regularity conditions, essentially the kind of regularity conditions that are needed to apply the policy gradient theorem or claim that Bellman's equation must hold for an optimal policy. Under those mild regularity conditions, and conditions 1 and 2 below, any stationary point of the policy gradient loss function must be optimal. So what are the conditions? The first is that the policy class is closed under policy improvement. Okay. You could write this in two ways. Basically, I'm saying that a policy iteration update could be attained within the policy class. Okay. Or equivalently here, this could be written in terms of these B functions, saying that the weighted policy iteration cost problem is minimized within the policy class. Now, the second condition that we need is some kind of structure like nice local structure that allows gradient descent to even make sense. Okay. And what we need is the weakest condition we can come up with is some notion of first order methods being able to solve the one period problem solved by policy iteration. So what is this? It says that this one period cost function has no suboptimal stationary points. All right. For example, in the last case, it's linear. In the remaining time, let me just make this slightly more concrete by looking at the linear quadratic control example that in many ways inspired this work. In linear quadratic control, we face the problem of minimizing the infinite horizon discounted sum of single stage costs that are convex quadratic functions of the state and action vectors. The state evolves according to this linear system here, okay, a controlled linear system. Now, it's known in classical that linear policies are optimal in this problem. So here, theta, I guess that we often view as a stacked vector, it's maybe better viewed as a matrix. And the action you play when in state S is just theta times S. Okay. There's real subtlety in asking whether we can find the optimal setting of theta via gradient descent, because the total loss function L is some messy non-convex function of theta. Okay. I have an expression for j pi here. It's a quadratic function of state, but a complex function of theta. And roughly speaking, the reason for this is that the state at time t involves taking the state at time 0 and multiplying it by this matrix here that somehow exhibits a compounding effect of changes of theta over time through this raising to the power t here. Okay. But policy iteration solves linear quadratic control very effectively. So here, the one-stage problem considered by policy iteration is just a quadratic function of A. Okay. Theta here is fixed, it's down here, and we're optimizing over actions A, and we get a one-period convex quadratic cost function. Okay. So let's check our conditions. Is the policy class closed under policy iteration updates? Well, yes. Starting with a linear policy, we get back a convex quadratic policy iteration cost function. And you can just check by differentiating that the optimal policy, that the policy iteration update is again solved by a linear policy. Okay. Now, the second condition also holds here. Because this is a quadratic problem, the one-stage problem has no suboptimal stationary points. Okay. I'll sort of skip the proof since I'm running out of time. I'll mention that sort of the problem with the bad example we showed before is that the policy class was not closed. Okay, so this really is a dividing line between the good and the bad examples. Sort of as I close, I think that we have now conveyed maybe the main insight in this work, but the paper itself treats a number of extensions with more depth. So for example, we look at a curious case of non-stationary policies and show that in that case, the policy class does not actually need to be closed. It's enough that the policy class contains the optimal policy. We look at a classes where the policy class is not closed, but somehow is rich enough that you could almost solve the policy iteration problems within the policy class. And then extend that to understanding how error is going to transfer to the quality of stationary points. Now, lastly, we look at convergence rates, essentially by showing that gradient dominance properties of the loss function of the policy iteration problem, implied, for example, by convexity of the policy iteration problem, transfer into gradient dominance properties of the multi-period loss. And finally, we look at the kind of special case of finite state inaction problems where one can show that policy gradient methods are really fast. So I guess these extensions are omitted from this talk mostly due to time, because I think it's more important to focus on the main insight first. But I'm happy to talk about some of them during the kind of extended questions during the controversial part. All right, thank you.
We're getting better at this, eh?
That's the best virtual clap I've seen so far. It's pretty good.
Yeah, there's a lot of clap messages in the chat as well.
Yeah, it's just rolling.
Yeah, well deserved. Thanks for the fantastic talk. So, well, I guess we're going to have questions about the proof and these extensions in a bit. So let me just look at the list of, oh my God, okay, there's lots of questions. Yeah. Right, so there was a question around the beginning regarding this initial distribution by Abraham Vinod. So I don't know if he's still here and if he's willing to ask his question.
Yeah, hi. Thank you for the nice talk. I was actually curious on when you scalarize the multi-object problem using this restart distribution, how sensitive is the choice of the restart distribution on the performance? How easy is it easy to design that?
Great. So I think that's a really central question and sort of a central next step. So we do sort of in the extensions, there's some discussion of how results and bounds depend on the initial distribution. There's this hard to interpret constant k rho that we provide some bounds on. Now, kappa rho. I think that you know, what's done in practice sometimes is that kind of in an engineering lab, people will make sure to design a sequence of diverse tasks on which they train you know, a grasping arm or something when they're running policy gradient methods. And somehow that's critical. I think that plays the role of the initial distribution rho. And you know, there is some question of whether we can take the grad students out of that picture and in a more automated way, maybe adaptively generate these rows. And yeah.
Yeah, so I myself have a similar question along these lines. So I don't exactly remember your conditions. Can you show them again? So did you have like a for all new quantifier in there?
Yes.
And is that like easy to ensure?
Great. So
I guess it's a little bit further down.
Where was it?
Yeah, right after this. Right, so you need this condition to hold for every single new and for every single policy. So like how much of this can you relax? Maybe is it enough for this to hold in the initial policy that you're starting from, and from that point on, you're always going to be improving, and under some distribution, for example, like the stationary distribution of the optimal policy or something?
Got it. So yeah, that's a great question. You know, I think that some of it's almost inherent. Now, I think that you really only need to satisfy this at the news that are induced by policies you play.
Right, yeah.
So that extension would be very easy. So the new that is the occupancy measure on the state of a policy you're at.
Mhm.
That's really what you need here. Now, it's somewhat tough though to get a handle on what those might be, and I think it's not going to be enough that it's the occupancy measure of an optimal policy.
Yeah,
Unfortunately.
that sounds unlikely. Yeah, but I guess it can be like the set of occupancy measures that is included, that is somehow induced by the policy class.
That's
I
right.
guess that should be enough, right?
Yeah, that's great. And I think it would be, I think that everything we've done would go through exactly with that set.
Right, great. So Nan Jiang has a question, which I guess it's like a little similar, but
yeah, I mean, basically, actually, part of the question was already answered by Dan's extension result, because I was about to ask, because CPI had this, it doesn't require rho to be completely have full support, but just the concentrability between optimal policy and rho is finite, but that's exactly what your kappa rho does. I also want to comment that CPI's analysis also hints at this closure property, because it's a pretty abstract algorithm, right? It tells you to do basically a little bit of one-step policy improvement and then mix it with your current policy. But it doesn't tell you like, it doesn't say, oh, what if that doesn't fall into our policy class? Well, if it doesn't fall into your policy class, you do a projection. And if your projection is lossless, that's basically like closure, right? So related to that, I want to ask, like, is there more deeper connection / differences between the CPI analysis and this work?
Yeah, that's a great question. I mean, I think the connections certainly are deep. The so I think in some ways maybe we're generalizing the insight there. So in some ways the CPI proof is like you literally move on the direction, the line segment connecting to a policy iteration update, and you move carefully in that direction. Now, one challenge that we ran into, I mean, maybe this is getting too into the weeds, but it's question time. One challenge we ran into is for things like threshold policies in optimal stopping, you cannot move along that line segment. Okay. And that's sort of what led to something more like this second condition here for showing the quality of stationary points. So basically CPI would not handle something like threshold policies. The other sort of separation, I guess, is that in some of these problems, the per stage cost is not linear in the kind of inaction probabilities. Instead, it's some kind of structured function of a vector action. And so you need to think about how that is going to affect the CPI proof. Yeah.
Yeah,
but
thanks. Thanks for a very good answer. I have a separate question, but I should let others ask first.
Okay, thanks. It's nice to virtually meet you, Nan.
Yep, me too, eventually.
Yeah, so actually Sharan Vaswani had a question. You wanted to say the same, Gary, I guess. So Sharan, are you with us? Like, can you ask your question? Do you have a mic?
Hi, yes. So what breaks if we try to do the stochastic gradient case? Because these results are like landscape type results, right?
Yeah, great. So I think what you need, so first, I guess stochastic gradients may affect rates. Now, beyond that, I guess what you just need is enough regularity such that you can apply something like a result from the stochastic approximation literature to say that you reach a stationary point via some kind of stochastic gradient descent. Now, there's sort of our motivation in only thinking about the landscape is that separately, there's this huge literature and a huge community right now actively studying how quickly one can reach stationary points by some version of stochastic gradient descent. And I sort of believe that if you applied one of those on top of this, it would give you asymptotic convergence. But we haven't carefully checked how that works in every one of these problems.
I see. And another quick question. So in neural network land, we have seen that the landscape can kind of be improved if you just massively over-parameterize things. So in your case, if the policy is like crazily over-parameterized, does it help with the convergence?
Yeah, it's a good question. In some sense, this closure condition, which I guess I lost, this closure condition, I think, is really saying that the policy class has to be rich enough. So it ends up being something that is satisfied if the policy is over-parameterized. I guess but over-parameterization is not a free lunch. Somehow neural networks also have an inductive bias that we don't maybe well understand that points you to particular minima over here. So I'm not sure, despite the fact that neural networks are heavily over-parameterized, I don't think the right understanding should be that they're always closed.
I see. Okay, awesome. Thank you.
Yeah.
So we had a question from Massimiliano Esposito. So he says, and I also remember that, the previous version of the paper had this condition on the action value function that the action, like that there should be a convexity of the action value function in the action space.
Yes.
Did you do something with that in the new work, or is that still around, or like that was kind of the second condition, I guess?
Good question.
That, right?
So I think that what happened in the new version of the work is that we relaxed that to be just a comment about the stationary points of the one period problems. Now, when you get when you have something like the convexity of the Q function in the action, and further convexity of the Q function, the Q function's action in some sense in the policy parameter, that's what was leading to this gradient dominance. So somehow the stronger condition is buying you more in some of those examples.
Mm.
So it's not lost, but it moved to the extensions.
Mm-hmm. Okay, I do have my own question. I didn't see the new paper, but you mentioned the result that is of considerable interest for me, which is that you get geometric convergence rates for the tabular case. With some colleagues, we've been working in similar directions. So I'm really curious about what this result is. So can you tell us some details about it?
In this one?
Yes.
Yes. Sure. I don't have many details here.
So is this for just the plane parameterization, no parameterization case with projections?
Good. Yeah. So it's for
Yeah.
the okay. It's mostly for the plane parameterization case with the full class of stochastic policies. The only sort of exception there is that we do look at something like mirror descent, which turns out to kind of match natural gradient descent in this case with the class of. So somehow mirror descent in the natural parameterization in this very special case is kind of the same as natural gradient descent with the softmax.
So we know that Is it the same thing as what is in Alex's paper? They say that, like they point out that, but that's for the softmax parameter.
Yeah, so that's for the softmax parameterization. So somehow, I guess what they've pointed out is that the softmax parameterization is the same as in that case with a natural gradient descent is the same as mirror descent. And so by studying mirror descent with the natural parameterization, we're effectively also providing a result about this.
Right, so that's actually not exactly mirror descent, but rather this MDP expert or TRPO or polytext or like whatever you like to call it. It's not exactly mirror descent, but it's a similar, it's a mirror descent flavored analysis. Yeah.
Yeah, it's a different regularizer kind of it's a weighted regularizer.
So there was a previous paper which was like the Alex paper that gave a 1/t rate for this case. So you're improving that to exponential rate.
Yeah, so this part of the paper, I should caveat, this part was not simultaneous work. This is directly inspired by their paper,
right?
And leverages it. And I think the basic point that we're making is that these one period problems in this case. So somehow the approach we've taken is to reduce studying gradient descent on the many period loss function to studying gradient descent on the one period loss function. And in this case, gradient descent on the one period loss function is sort of trivial. You're just picking the right corner of the simplex and moving there.
Right.
And because of that, with the right step sizes, policy gradient almost reduces to policy iteration. And that's all we did, is sort of formalize that if you, say, use line search to pick the step size, you wind up with policy iteration rates and analysis.
To throw in more names, this is like Frank Wolf too.
Yes. So Frank Wolf or this. So this should
Okay, good.
I don't know how widely this is known, but I think it's cool that Frank Wolf is policy iteration in this case. It's soft policy iteration.
Right. Yeah.
Yeah. It's pretty deep.
Okay. Yeah.
So I'll be interested in what you guys are working on, Chaba, if you want to talk offline sometime.
Yeah, we can talk more. It's an archive. We also have geometry grades, but it's for the softmax parameterization and entropy regularization.
Okay.
Yeah.
Should look.
Yeah.
Cool.
Right. So I guess this is starting to sound more and more like the off-record thing.
Seems to.
Yeah.
So I guess maybe let's move on to that one. Let's thank Dan one more time again for his talk. And yeah, that's good.
Okay. I stopped recording. Thank you, Dan.
Thank you.